Lesson 0.2, Factoring Review. In this lesson, you will use the structure of an expression to identify ways to rewrite it. In other words, given an expression, factor it. So let's get started. So imagine you're walking down the street in some big city, and some fancy looking guy in some big poofy hat walks up to you, offers you $1 million to factor an expression. Well, the first thing you're going to need to know is how many terms does it have? Are there 2 terms, 3 terms, or are there more than 3 terms? If there's 2 terms, you're going to use the GCF method. The thing about the GCF method, though, is that you're always going to use the GCF method. If there are 3 terms, you're going to use the GCF method. That's factoring out the greatest common factor. However many terms you have, look at all the terms. If you have something in common, factor it out. The key thing to remember, though, is that if you have 3 terms or more than 3 terms, once you factored out the GCF, you still have more work to do. With 3 terms, the most common technique is going to be what I like to call the AC method. You may know it by a different name, but I call it the AC method because it reminds me on what the first step is going to be. When there's more than 3 terms, after you've used the GCF method to see if there's anything that you can pull out, then I like to say we go into some more fancy algebraic techniques that may include grouping, that may include something called the rational root theorem, that may include giving up and crawling into a fetal position, something more advanced than just what you've learned in Algebra 1 and Algebra 2. So let's start with the GCF method. Notice here we have 2 terms. For the first question, 6x squared minus 3x. Again, I have 2 terms. The only method of factoring I can try is the GCF method. Step 1 is identify the GCF, the greatest common factor. Between 6x squared and 3x, what do they have in common? Between 6 and 3, their common factor would of course just be 3. Between x squared and x, their common factor would be x. So the GCF would be 3x. When I'm factoring by GCF, I put the 3x out front, and then I ask myself what remains. One way to think about this is to ask yourself, if I were to distribute 3x onto the inside, I need to get back to the original. So 3x times what gives you 6x squared? Well, 3x times 2x will give you 6x squared. And 3x times what gives you negative 3x? Well, 3x times negative 1 gives you negative 3x. Again, you can always check your factoring by re-multiplying to see if you get back to your original question. Now, what I want you to do is pause here and try the second problem on your own. Hit play when you're ready. All right, looking at the second problem, negative 5x cubed plus 5x squared. Again, there are 2 terms, so the factoring method will be GCF. What is the GCF between negative 5x cubed and 5x squared? Well, you may have said that the GCF is 5x squared. If you didn't say 5x squared, put a pin in it, and we'll come back to it a little bit later. So I put the 5x squared on the outside. That would leave negative x plus 1 on the inside. And although this is an acceptable answer, this is not the answer I want. Here's the thing. That leading negative. Anytime I have a leading negative, I want you to make that part of the GCF. If you have a leading negative, pull out the leading negative. So because there's a negative in the front of the problem, I'm going to make the GCF, instead of it 5x squared, it's going to be negative 5x squared. And if the GCF is negative 5x squared, that makes the inside positive x minus 1. Again, double check by distributing. Negative 5x squared times x gives you negative 5x cubed. Negative 5x squared times negative 1 gives you positive 5x squared. Pulling out the leading negative is going to change the signs on the inside. Now again, this is not a crucial step on this problem, but as we move forward, anytime you're pulling out a GCF as part of a bigger problem, you're going to need to pull out that leading negative in order for things to work out the way they need to work out. Moral of the story, pull out leading negatives. Always pull out leading negatives. All right, here's something interesting. This time we have 3 terms. That's fine, okay. Step 1, 100% of the time, look for a GCF. We have a 4, 8, and a 5. Notice between 4, 8, and 5, there are no common factors. Of course, 5 is a prime number, so it's just 1 and 5. 1 is never interesting when you're factoring. Never try to pull out a 1 when you're factoring, unless of course it's important to pull out a 1, because always remember that math teachers lie. We say one thing, but then 10 minutes later we say, oh, ignore that thing that I just said because we're going to do exactly what I said not to do. Never pull out a 1 when you're factoring, unless it's important to pull out a 1 when you're factoring. Stay tuned. So the only interesting thing about 5 is 5 itself, and I know 5 doesn't go into 8 or 4, so there's no need to look any further for a numerical GCF. And of course, we also have x squared, x, and then no variable. Since there's no variable on this one, you can't pull any variables out at all, so there is no GCF on this problem, which means the GCF method is not going to work. That doesn't mean we're done, that just means move on to the next level of factoring, and that would of course be the AC method. Now, again, do not use the AC method until after you've looked for a GCF. There's a technique that I'm going to be going over in this lesson that if you do not look for a GCF first, the method will not work. In general, the first way I use the AC method, it'll work just fine with or without the GCF method, but to say it's fully factored, you have to use the GCF method first. Even if there's no GCF, you have to at least look for a GCF. So, factoring a quadratic trinomial using the AC method. I'm going to go over two options. The first option, again, although you may not know this as named the AC method, because that's not actually an official name, it's just kind of what I call it, and a lot of people I know call it that as well, because it helps you recognize what method that we're using. As we're going through, hopefully you recognize this method as one that you have been using before, but I'm actually only going to show you this method as a way of saying, hey, this is how the method is done, but I'm never actually going to do it this way. Option 2 is going to be the shortcut method that I only teach to my pre-calculus level students. So, first off, recognize that a quadratic is always of the form ax squared plus bx plus c. A is the coefficient of the quadratic term, b is the coefficient of the linear term, and c is the constant term. If the terms are out of order, reorder them so that it's in descending order, x squared, then x, then the constant term. So based on what I have here, a would be 4, b would be 8, and c would be -5. So the AC method begins with multiplying a by c, hence the name, the AC method. So a times c, 4 times -5, gives us -20. Moving on. Step 2. Find factors of AC, which we just found to be -20, that add up to the middle term b. Notice not bx, just b. b is 8. So I need factors of -20 that are going to add up to 8. Now, this is the part of factoring where it really comes down to, do you know how to factor? And I'm not talking algebraic factoring, but elementary factoring. Do you know your times tables? If you don't know your times tables, there is absolutely nothing I can do for you. At this point, you are stuck. You cannot go any further in mathematics if you don't know your times tables. Just like if you don't know basic vocabulary, there's no hope in trying to read a book. If you don't know your times tables, you cannot do algebra. So hopefully you know your times tables. And hopefully the goal is that if you look at this statement right here, factors of -20 that add up to 8, you automatically know what those two factors are without much thought. Now, I will concede that if you do need to list out your factors to test it out, that's perfectly fine for now. But the goal, of course, will be to simply look at this and write down the two answers. So if you do need to list them out, I recommend doing it methodically, going in order. Start with the smaller factors and build yourself up. So 20, you can always start with 1. So 1 and 20. After 1 comes 2, 2 and 10. After 2 comes 3, 3 doesn't go into 20, so move on to 4, 4 and 5. Now after 4 would come 5, which is already there, so we know we're done. By going in order like that, you're not randomly trying to think off the top of your head, what are all the factors? You're going in order, 1, 2, 3, 4, 5, 6. As soon as you get to a number that's already listed, you know that you found all the factors. Now, the problem here, of course, is that it wasn't 20, it was -20. Two positive numbers do not multiply to give you a -20. One of these numbers has to be negative. Well, we can use this piece of information as well. The fact that it has to add to a positive means the larger number would have to be positive and the smaller number would have to be negative. Multiply to a negative means one of the numbers is negative. Add to a positive means the larger number would be positive. So now, eyeball it, which one of these pairs adds to positive 8? Well, of course, it would be negative 2 and 10. Again, that whole process should take you about 5 to 10 seconds on any random factoring problem. If you're taking longer than 5 to 10 seconds, you need more practice. So again, to recap, we started by multiplying a times c, which was negative 20. Then we found factors of ac that add to the b value, 8, which was negative 2 and 10. Step 3, break up that b term. So what was previously positive 8x, we're going to break it up using the two numbers that we found right here, negative 2 and positive 10. So instead of being 8x in the middle, it's negative 2x plus positive 10x. Now, important thing to note, it does not matter which order you write this in. Positive 10x minus 2x is the same thing as minus 2x plus 10x. It does not matter. You can write it in either order. You'll get the same answer in the end, and I'll show you that after we've gone through it all the way. So I'm going to use negative 2x plus 10x as I move on to the final step. Group and find GCF. So even though we're using the AC method, the GCF method is built into this process as well. Now, if you need a refresher, grouping involves grouping the first two terms and grouping the second two terms. So if I look at the first two terms and ask myself, what's the GCF? 4x squared minus 2x. Of course, the GCF would be 2x. And on the second two terms, 10x minus 5, the GCF would be 5. So what I'm going to do is I'm going to pull out the 2x on the first pair. I'm going to pull out the positive 5 on the second pair. And when I pull out the 2x, that leaves behind 2x minus 1. When I pull out the 5, that leaves behind 2x minus 1. And that right there tells you that you're doing this correctly. Inside the parentheses, they should have exactly the same thing. If I don't have exactly the same thing inside the parentheses, then I need to stop what I'm doing and either A, find my error, or B, just start over completely. If you're doing this properly, then I should have the same thing inside the parentheses. If I don't have the same thing inside the parentheses, that means I picked the wrong numbers on that previous step. The factors of AC that add up to B, I picked the wrong numbers, or I simply made an error factoring out the GCF on this step. But I made an error somewhere. I should have the same thing inside the parentheses. Close is not the same. It's either exactly the same or it's wrong. Now, because I have the same thing, 2x minus 1, 2x minus 1 on both of these, what I can actually do is kind of think of this as one term unto itself, and this as one term unto itself. And I ask myself, using the GCF method, what does this guy and this guy have in common? Well, 2x minus 1. So 2x minus 1 is a GCF between this whole guy and this whole guy, which means I can pull out the entire factor, 2x minus 1, putting it on the outside, which leaves behind 2x plus 5 as the other factor. So if I get rid of the 2x minus 1, get rid of the 2x minus 1, put it on the outside, 2x plus 5 is what's left on the inside. And that right there would be the factorization of this polynomial. Again, I can always check my work by simply redistributing. 2x times 2x gives me 4x squared. Negative 1 times 5 gives me my negative 5. And then the 2x times 5 would be 10x. Negative 1 times 2x would be negative 2x. And of course, 10x minus 2x gives me the 8x in the middle. I can always remultiply to check to make sure that I got the right answer. Now, just to confirm that the order of that negative 2x plus 10x doesn't matter, notice if I switch it up and make it 10x minus 2, notice how things change. Instead of it being 4x squared minus 2x, it's now 4x squared plus 10x as my first pair. Pull out the GCF, I get 2x, leaves behind 2x plus 5. On the second pair, hey, remember how I said never pull out a 1 unless it matters? Here's where pulling out a 1 actually matters, because between 2 and 5, there's nothing in common, but I have to pull something out, so I'm going to put a 1. Also notice, in those two terms, we have a leading negative, so I pulled out the leading negative. So between negative 2x minus 5, my GCF was negative 1. I have to pull out something, so I pulled out a 1. And because there's a leading negative, I have to pull out that negative. When I pull out that negative, that leaves behind 2x plus 5. If I didn't pull out that negative, it would not have said 2x plus 5, which would not have matched what I have over here, which means this process would not have worked. I have to pull out leading negatives when I have a leading negative. So inside 2x plus 5, inside 2x plus 5, which means this worked. So 2x plus 5 is one of my factors, and 2x minus 1 is my other factor, which is exactly the same thing I got the first way. Now, the method I just went over, the AC method, is a tried and true method that works 100% of the time. But as you move forward in mathematics, it's really helpful to have some shortcuts in your back pocket. You don't want to be taking 5 minutes on a factoring problem when you could be taking 30 seconds on a factoring problem. Factoring is never going to be the end-all be-all to upper-level math problems. It's simply one small step in a much bigger problem. Which brings us to the modified AC method. Now, with the modified AC method, it is even more important to make sure that you check for a GCF first. If you do not check for a GCF first, you can do everything correctly and still get the wrong answer. Because if there was a GCF that needed to be pulled out, you will not get the right answer. So always check for a GCF first. Always check for a GCF first. If you don't pull out a GCF when there was a GCF, you will not get the correct answer. So step 1, multiply A and C, we get negative 20. Step 2, find factors of AC that add to B, negative 2 and 10. That process has not changed. The first 2 steps are exactly the same. What changes is as we move on to step 3, which previously would have been to break up the B term and then step 4, factor by grouping, we're just going to cut to the chase. We're going to go straight to the answer. Step 3, I like to call this 2 wrongs make a right. Because I'm factoring a quadratic trinomial, I know that my final answer is going to be a double bubble of 2 binomials. I know I'm going to be multiplying 2 factors of 2 terms apiece. So let's go straight to that double bubble. Now, I'm going to look at this 4x squared term first, and what I'm going to do is I'm going to ignore the square, and I'm going to take the 4x on its own. And I'm going to put that 4x in both bubbles. I'm going to lead both bubbles with 4x, not 4x squared, but 4x. But there's a problem with that because, of course, I know that when I re-multiply these 2 binomials to get back to the original, I know that 4x times 4x is supposed to give me the original 4x squared. But of course, 4x times 4x does not give me 4x squared. So this is wrong. This is incorrect. We're going to call that wrong number 1. Now moving on. For the other 2 spaces in the double bubble, that negative 2 and 10 that I found earlier, I'm going to go ahead and sprinkle those in right here. But again, negative 2 times 10 should give me this final number of negative 5. This number times this number should give you that number, just like this number times this number should give you that number. Negative 2 times 10, let me double check, yep, does not equal negative 5, so this is wrong number 2. I have made 2 wrongs, but of course, as we all know, 2 wrongs always make a right. Step 4, I'm going to take my 2 wrongs within my double bubble and I'm going to reduce. The way I reduce is the same way as if I'm reducing a fraction. Within each factor, aka fraction, I'm going to go ahead and divide by their common factor. Between 4x and 2, they have a common factor of 2, so I'm going to go ahead and divide both of those by 2, and then I'm going to look at the 4x and the 10. They happen to also coincidentally have a common factor of 2, so I'm going to divide that out as well. Notice I'm not factoring out 2, I'm dividing out 2. I'm reducing. I'm getting rid of that 2 completely. Do not factor out that 2 and put it up front. That will be the wrong answer. These are mistakes. They should not have ever been there, so I need to cover up that mistake by getting rid of it completely. So when I divide the first factor by 2 and the second factor by 2, what I'm going to be left with is the correct solution of 2x minus 1 and 2x plus 5. Remember, this is the same one that we factored earlier using the regular AC method, so we already know the correct answer is 2x minus 1 and 2x plus 5. But notice, with this method, I got there without doing the whole grouping process. I went straight to the double bubble. I made purposeful mistakes, and then I corrected those purposeful mistakes using a specific process. And again, this technique also works 100% of the time. As long as I pull out the GCF first, if there is a GCF on the original problem, this method will always work. And it's always significantly quicker than the regular AC method. Now, just for kicks, here's why it works. Consider that original problem, 4x squared plus 8x minus 5. For no reason whatsoever other than I know how this is going to work out, I'm going to multiply that whole thing by 4. I picked 4 because I wanted to match whatever the a value was itself. So the a value was 4, so I'm going to multiply everything by 4. And when I do that, I get 16x squared plus 32x minus 20. But again, because I picked 4, that 16 is really just 4 squared, which means 16x squared is itself 4x squared, or 4x times 4x. Now notice, because I multiplied every term by 4, there's a 4x hidden within this 32x as well. So even though I had just multiplied the 4 through, I'm going to go ahead and break it up one more time into 8 times 4x, so that this 4x and that 4x match. That negative 20, on the other hand, I'm just going to leave on its own. It doesn't need to change. Now, in order to simplify the way this looks, I'm going to go ahead and define m to be 4x. So instead of saying 4x squared plus 8 times 4x minus 20, I could just say m squared plus 8m minus 20. And this right here is a much easier factoring problem because there's no a value up here. I can easily just go straight to my double bubble because m times m gives me m squared. Factors of negative 20 that give you 8 would be negative 2 and 10. So negative 2 plus 10 gives you 8. Negative 2 times 10 gives you negative 20. So I know this is the factorization for that quick and easy factoring problem. But again, m wasn't the original problem. M is 4x. So if I take the m minus 2 and the m plus 10 and replace m with 4x, I get this statement, which may look familiar to you. Now in this case, I'm not using any shortcut techniques. I'm factoring this properly, which means out of the first 2 terms, I can pull out a 2, and out of the second 2 terms, I can pull out a 2. Multiplying everything together, keep in mind 2 times this times 2 times that is the same thing as 2 times 2 times this times that. So really, I could just rewrite this as 4 times 2x minus 1 times 2x plus 5. And then I remember at the very beginning of the problem, I multiplied by 4. I can't just change a problem. That doesn't make any sense. I can't just multiply an expression times 4 and call any of this equivalent to what I originally started with, unless at the end of the problem, I divide by 4. So at the beginning of the problem, I multiplied by 4 in order to make things work out a particular way I wanted them to work out. And then at the end of the problem, I divide by 4 in order to get rid of the evidence that I ever multiplied by 4 to begin with. Which is why in that shortcut method, I don't factor out those 2's, I just divide them out because they didn't belong in the problem to begin with. So now's your chance to try this. Here are 4 problems that I want you to factor. Take a stab at each one, and I'd like you to try the new method, the 2 wrongs make a right method. Now, if you don't like that method and you want to go back to whatever method you're comfortable using, that's fine as long as you can run through it quickly and easily. If you're taking 7 minutes on a factoring problem, I need you to stop doing it that way and try it a different way. If you're making mistakes frequently, I need you to stop doing it that way and try it a different way. But if you are quick and efficient with factoring problems, as long as no matter what factor problem I give you, you can get it done in 30 to 45 seconds, then I'm fine with it. Continue with whatever you're doing. Otherwise, I encourage you to try this new method because if you do this new method correctly, you'll always be under that 30 to 45 second marker for doing a factoring problem. So again, try each of these out one at a time, pause the video, and hit play when you're ready to go over them. All right, let's take a look at these. So starting with the first one first, 2x squared minus x minus 10. Again, I'm going to be using the new 2 wrongs make a right method, but I'm still going to be starting with a times c. So 2 times negative 10 gives me negative 20. Factors of negative 20 that add to negative 1. Now, if you had to list out the factors of negative 20, that's fine for now, but hopefully you should be looking at 20 and 1 and thinking to yourself, what factors of 20 are 1 unit apart? Of course, that would be 5 and 4. In order to add to a negative, the larger number would have to be negative, so it's going to be -5 and +4. I then go straight to my double bubble. In the first part of the double bubble, the variable term, I'm going to look at that 2x squared. I'm going to get rid of the square. I'm going to write 2x in both of them. Again, I know this can't be possibly right, but I'm going to make that correction later on. Then I'm going to take the -5 and the 4. I'm going to sprinkle those in. I now have 2x minus 5 and 2x plus 4. I look at each factor independently. I see that with the 2x minus 5, there's nothing in common, so that one is already fully reduced. I look over here, 2x plus 4, that can be divided by 2, so I'll do so. Divide by 2, and that's going to give me my final answer of 2x minus 5 and 1x plus 2. Again, I can always double check my answer by redistributing. 2x times x gives me 2x squared. -5 times 2 gives me -10. And if I do the outside inside, 2x times 2 gives me 4x. Minus 5x would give me the -1x in the middle. Now looking at the next one, x squared minus 5x plus 6. Starting with a times c, a of course is +1. So 1 times 6 gives me 6, factors of 6 that add to the b term, -5. Always be careful with this one, getting from 6 to 5. It could be 1 and 6, it could be 2 and 3, depending on where the positives and negatives line up. I know to multiply to a positive and add to a negative, it's going to have to be a double negative in here, so it's going to end up being 2 and 3. -2, -3. Double bubble. Look at the x squared term, drop the square. We're going to put x and x in both bubbles, and then we'll put -3 and -2 also in both bubbles. Now in this case, 1x minus 3 cannot be reduced. 1x minus 2 cannot be reduced, which means final answer, x minus 3, x minus 2. Anytime you have an a value of 1, you know this is going to be a pretty straightforward problem. All right, now let's look at the next one. So 30x squared plus 25x minus 30. You may have looked at this one and saw, starting 30 times 30, which of course is 900, factors of 900 that add to 25. I don't want to do this. Well, that's usually your first clue that you're probably doing it the wrong way. Anytime you look at a problem and say to yourself, oof, this looks difficult, I don't want to do this, ask yourself, hey, maybe I'm missing something that would make this problem a whole lot easier. And in this case, it wouldn't be just easier. If you don't do this, you're going to get the wrong answer. GCF. You have to look for a GCF first. Between 30, 25, and 30, you have a GCF of 5. So start by pulling out the GCF. When I pull out a 5, that leaves behind 6x squared plus 5x minus 6. Smaller numbers make this a much more manageable problem. So continuing with my 2 wrongs make a right method. Now, as I continue, that 5 on the outside has been factored. It can be ignored until we get to the end of the problem. I'm factoring 6x squared plus 5x minus 6 from this point forward. So a is 6, c is -6, AC is -36. I'm looking for factors of -36 that add to 5. After you think about this for a couple of seconds, you should be thinking about 9 and 4 that could combine to give you 5, as long as it's a +9 and a -4. So double bubble. Again, we're not looking at the original question, we're looking at this secondary question, 6x squared, drop the square, 6x in both bubbles. -4 and 9 sprinkled in as well, and now reduce. In the first pair, 6x minus 4, we can divide by 2. In the second pair, 6x plus 9, we can divide by 3. So when I do that, 6x minus 4 becomes 3x minus 2. 6x plus 9 becomes 2x plus 3. But this isn't my final answer. My final answer also has to include that original GCF of 5. So 5 times 3x minus 2 times 2x plus 3 would get me back to the original stated problem. Don't pull out that GCF and then forget to state it as one of your factors. The F in GCF does stand for factor. And the last one, 4x squared minus 9. Now, if you look at this and recognize it, great. This is something that you should recognize, and you should automatically know how to factor this when it comes up. If not, let's go through the process. 4x squared minus 9, notice there's a missing term. The missing term is the b term. Now, anytime you're missing a term, feel free to just put in a placeholder. In this case, it would be 0x. 0x is the same thing as saying 0 itself, so it's just there as a placeholder, just to fill in the space where the term should have been without changing the meaning of the problem. If I go through the modified AC method again, 4 times -9 is -36. Factors of -36 that add up to the b value, which happens to be 0 in this case, would be 6 and -6. Double bubble, 4x squared becomes 4x and 4x. -6 and 6 go in their places, and then when I reduce, 4 and 6 can be divided by 2, so I get 2x minus 3, 2x plus 3. Now, if you didn't recognize this from the very beginning of this problem, shame on you, you haven't been paying attention in Algebra 2. If you do recognize this, great, you know this as the difference of squares. Do not let me see you ever factoring a difference of squares using this method. Shame on you if you ever factor a difference of squares using this method. A difference of squares is a special case that comes up over and over and over again. 4x squared is a perfect square. It's 2x times 2x. 9 is a perfect square. It's 3 times 3. It is subtracting, aka difference. So anytime you have a difference of squares, please just go straight to the answer. 4x squared is 2x times 2x. 9 is 3 times 3. 1 has to be positive, 1 has to be negative. It doesn't matter what order. 4x squared minus 9, difference of squares, 2x minus 3, 2x plus 3. So while we're on the topic, let's double down on that. Here are a bunch of problems that I want you to factor using the difference of squares technique. Pause here, hit play when you're ready. 16x squared minus 25. Hopefully you recognize 16x squared is a perfect square. That's 4x times itself. 25 is 5 times itself, which means we go straight to the answer of 4x minus 5, 4x plus 5. X squared minus 9, that's x times itself, that's 7 times itself. So x minus 7, x plus 7. Again, it doesn't matter the pluses and minuses, which order that you write it in, it's the same thing either way, because multiplication can be done in any order. X squared plus 100, x times itself, 10 times itself. But here's the issue. It says x squared plus 100. Plus, not minus, plus. This is a sum of squares, not a difference of squares, which means it's actually not factorable. A sum of squares is prime. It's not factorable. You cannot break this up into two factors that multiply to give you x squared plus 100. If we had done this the long way and we put in the middle term 0x as a placeholder and asked ourselves factors of 100 that add to 0, well, because it's got to be a positive 100, it's either positive 10, or negative 10, negative 10, which do not add up to 0. You have to have the positive and negative in order to get the 0 in the middle. So when it's a sum of squares, it's not factorable. There are no factors of 100 that will add to give you 0. Feel free to think about it. You're not going to find any. And that's the thing about factoring. It's just as important to know what the factors are as to know that there are no factors. When you see something that's not doable, don't stare at it for 20 minutes trying to figure out the answer. Just say, hey, this one's not doable, and move on to the next one, such as 1 minus x to the fourth. Careful here. That doesn't say x squared. That's not a perfect square. Oh, yes, it is. X to the fourth is x squared times x squared. Any even exponent is a perfect square. Any even exponent is a perfect square. X to the 10th is x to the 5th times x to the 5th. X to the 20th is x to the 10th times x to the 10th. X to the 25th is not a perfect square because you can't break that into something times itself. So 1 minus x to the fourth must become 1 minus x squared and 1 plus x squared. Now always remember, you're not done until you're done. Hey, look at this right here, 1 minus x squared. Isn't that itself a difference of squares? Why, yes it is. 1 minus x squared would be 1 minus x, 1 plus x. And then 1 plus x squared, a sum of squares, cannot be factored. So on this one, it actually factors into 3 binomials. Here's another special case, x squared minus 10. Now, x squared is a perfect square, but 10 is not a perfect square. So here's the thing. If I ask you to factor x squared minus 10, you are welcome to say this is not factorable. If I were doing this the long way, I would be asking factors of negative 10 that add to 0, 0 being that middle placeholder term. Factors of negative 10 that add to 0, well, there aren't any. 1 and 10, 2 and 5, nothing is going to combine to give you 0. So I could perfectly correctly say x squared minus 10 is not factorable. But there's always ways around things, because of course 10 is a perfect square. It's the square root of 10 times the square root of 10. You can factor things into irrational factors. That is an option. You could do this. This would be a true statement. But generally, we don't do that. If it says factor, I generally don't want you to write it as irrational factors using radicals or imaginary numbers. Unless you have a clear reason that you would want to do that, then I don't suggest doing it. But you would not be wrong to say this. And the last one, you may notice that neither of these are perfect squares, but of course you also noticed rule number 1, always look for a GCF. In this case, we have a GCF of 2, and when we pull that out, it reveals a difference of squares, x squared minus 4, which factors into x minus 2x plus 2. Always be on the lookout for a difference of squares, because if it's there and you don't see it, I've got a problem with you. Now, there are more special cases than just difference of squares, as you were made aware of in earlier math courses. So I just want to remind you real quick of those rules. Now, of course, the first one, difference of squares, anything of the structure a squared minus b squared can be factored into a minus b, a plus b. Difference of cubes, a cubed minus b cubed, is a little bit more complex, as you can see. We still have the a minus b up front, but it's not just a plus b, it's actually a squared plus ab plus b squared. Now, the way I always remember this one is I think to myself, a cubed, well, that's just a times a, which of course is the same thing as saying a times a squared. When I see a cubed, what I'm going to do is in my mind break that into a and a squared, and I'm going to put that first and first, a and a squared. Same thing with b cubed. That's b and b squared. So there's b and b squared. And then whatever numbers I put right here, a and b, that gets multiplied together right here as your middle term. So a and a squared is your first term, b and b squared is your last term, and then the middle term is just whatever numbers you had right here multiplied together, a, b, a, b. And then the minus positive positive, just remember this, mop, M-O-P, mop. When you're done with a problem, you got to mop it up. Match, opposite, positive. Match, opposite, positive. So this said minus, so right here we're going to match minus, and then we're going to do the opposite of minus, and then we're going to do positive every single time. Match the given, opposite of the given, positive, positive, positive. Unlike the squares, where the difference of squares is something, but the sum of squares is not, with cubes, you can factor it either way. And we're going to use the same technique, a cubed, b cubed, and then mop it up. So a cubed breaks into a and a squared, b cubed breaks into b and b squared. Whatever these numbers say right here, we're going to multiply them together in the middle and then mop it up. Match, opposite, positive. Match the given, which was positive, and then opposite of the given, opposite of positive is negative, and then the third term is always positive. And then finally, the perfect square trinomial, which also comes up quite a bit. If you have something of the form a squared plus 2ab plus b squared, that's a perfect square which can be factored into a plus b, a plus b. A times a is a squared, b times b is b squared, a times b times a added together gives you 2ab. Now, of course, if it's something times itself, we could simply rewrite it as a plus b squared, just like this. Now, the perfect square trinomials are not always as easy to recognize as a difference of squares, a difference or a sum of cubes are. The perfect square trinomial, if you don't recognize something as being a perfect square, it's actually fine. You could still factor this the long way and get the right answer in the end. You just get to the end and realize, oh, this was a perfect square. The perfect square trinomial formula is basically something where if you happen to notice that the first term and the last term are perfect squares, check to see if the middle term is of the appropriate structure. You can go straight to the answer without doing any work whatsoever. And we'll look at that in just a second. For now, I want you to try factoring out a difference of cubes using the formula. Now, anytime you're trying to practice a formula, the goal should be don't look at the formula. Also, don't think of it as a formula. Think of it as a process. Go through the process over and over again until you memorize the process, not memorize the formula. So why don't you try this one, and if you get stuck, proceed with the video, and then I'll have another one for you to try after this one. So 8x cubed minus 27, I recognize this as a difference of cubes. 8x cubed would be 2x times 2x times 2x, or 2x cubed. 27 is, of course, 3 cubed. So now I'm going to go to my double bubble, but I'm going to remember the structure of a difference of cubes is that the first bubble has 2 terms, and the second bubble has 3 terms. And I remember that 2x cubed can be broken up into 2x times 2x squared. Now remember, it's not 2x squared, it's 2x times 2x, which means it's really 4x squared. Remember, the first term times the first term should give you the first original term. If 2x times 4x squared does not give you 8x cubed, you know you did it wrong. Then we'll do the 3's the same way. So I'll put a single 3 here, and I'll put a squared 3 here, which of course would be 9. Double check. 3 times 9 gives us 27. Notice I'm completely ignoring the minus in the middle because I'm going to mop that up at the end. Finally, the middle term in the 3-part bubble is always going to be whatever these two numbers are multiplied together. 2x times 3 gives us 6x. So now let's mop it up. The original was minus, so we're going to match, opposite, positive. Final answer. Again, you could always check your answer by redistributing, remultiplying this all out. Anytime I multiply a 2 by 3 multiplication problem, I'm going to get 6 terms overall, but you'll find that everything except for the first and the last term are going to cancel out. All right, here are 2 more problems. Why don't you try these on your own? Okay, x cubed plus 125, again, perfect cube, 125 is, of course, 5 cubed. This one is a sum of cubes, which remember for cubes is perfectly fine. If this was a sum of squares, we would say not factorable, but for a sum of cubes, that's perfectly fine. So, double bubble, 2 by 3. In the first bubble, we're going to put x in x squared, and then we're going to put 5 and 5 squared. And then in the middle, we're going to put whatever numbers these were right here. X and 5 would be 5x, and then mop it up. Match, opposite, positive. Now you might also be asking yourself, hey, wait a second. This is quadratic right here. Couldn't we try to factor this one further? Same thing up here. Couldn't we factor this further? Well, actually, you could try, but you're going to fail 100% of the time. The thing about the difference of sum and difference of cubes formula, this quadratic that you're left with will never be factorable. Factors of AC that add to B, in this case, there are none. There are no factors of 25 that add to -5. There are no factors of 36 that add to 6. Feel free to hunt for them. You're never going to find them. So rest assured, when you're doing a sum or a difference of cubes, that quadratic that you're left with is not going to be factorable. And the last one, 1 minus x to the 6th. 1 is 1 cubed, and x to the 6th would be x squared, x squared, x squared, or x squared cubed. So breaking it up, I'm going to put 1 times 1 squared. Here I'm going to put x squared times x squared squared. And the middle term will be whatever this guy times this guy is, so the middle term will be x squared. And then mop it up. We started with a minus, so match, opposite, positive. But not the final answer because, again, always be on the lookout. Hey, look at that. 1 minus x squared is a difference of squares, which means keep factoring. 1 minus x, 1 plus x would be the factorization for 1 minus x squared. And of course, 1 plus x squared plus x to the 4th, just like the other ones, is not going to be factorable, so I'm not even going to try. So here would be my final answer. All right, and finally, the perfect square trinomial. And again, this is one of those special cases that if you completely ignore, it's going to be perfectly fine. It's not, although if you recognize it, it'll save you time. If you don't recognize it, it's not that big of a deal. It's not something that comes up enough that it's going to make that big of a difference at the end of the day. I'll tell you, I often don't recognize a perfect square trinomial when it's presented to me. Although when I do happen to recognize it, great, I'm going to save a little bit of time, but I could easily do this one using either the AC method or the modified AC method and get the right answer. The key to recognizing a perfect square trinomial is step one, it's got to be a trinomial, 1, 2, 3 terms, so we're good there. And then two, the first and last terms need to be perfect squares. 4x squared is 2x times 2x, and 25 is 5 times 5. So the first and last terms are perfect squares. That's the first thing to recognize. Now, the middle term, in order for this to be a perfect square trinomial, has to be of the structure 2ab, where a is what's being squared here, and b is what's being squared here. So a would be 2x, and b would be 5. So ask yourself, if this is 2x squared and this is 5 squared, if I take that 2x and that 5, multiply them together and double it, do I get the middle term? If I do, then this is indeed a perfect square trinomial, which means my answer is 2x plus 5 quantity squared. So I don't have to go through the whole AC process. I don't have to go through the two wrongs make a right. If I recognize something as being a perfect square, in other words, square root of the first term, square root of the last term, multiplied together and doubled gives you the middle term, then I can go straight to the final answer. For instance, look at this one. See if you can factor this one. Okay, so first term is, of course, 5x squared. Last term is, of course, 3 squared. So if I multiply those together and double it, do I get the middle term? Now, this time we have a minus in there. That's fine. It's the minus, just like with the sum and difference of cubes, it really doesn't matter. We can deal with that separately. As long as the magnitude is correct, you're fine. 2 times 5 times 3 is indeed 30, so this is a perfect square. The difference with the minus is that we're just going to put the minus in the factor. So instead of it being 5x plus 3, it'll be 5x minus 3. And one more. Pause here, play when you're ready. So once again, I noticed that the first and last terms are perfect squares. That would be 3x quantity squared. That would be 2 quantity squared. If I multiply them together and double it, do I get the middle term? Well, actually this time, no, I don't get the middle term, because 2 times 3 times 2 would give you 12, not 10, which means this is not a perfect square trinomial, which means we can't factor it as a perfect square trinomial. That doesn't mean give up, that means try something else. This is still a trinomial, which means we can use the AC method. So 9 times 4 gives you 36. I need factors of 36 that add to negative 10. Factors of 36 that add to negative 10, well, that would be negative 1 and negative 36, negative 2 and 18, negative 3 and negative 12, negative 4 and 9, negative 6 and 6. None of these are going to add to negative 10. Don't stare at it until you can think of the answer. Recognize that there is no answer. If you can't find factors of AC that add to B, you're done. This one is prime. This one is not factorable. So there you have a extremely brief review of the main factoring techniques that we're going to be using in this course. I didn't go significantly into depth into anything, and of course you're definitely going to need to practice all of those techniques frequently, not just tonight, but over and over and over again throughout the rest of your mathematical career. Now, if there's something that you're still struggling with, if there's a topic that you'd like me to go more in depth into, option one is go on the Google machine, type in GCF method or difference of cubes, whatever method that you weren't sure about, type it into the Google machine and look up more information. There are literally millions of videos out there, not just the one that you're watching right now. Or come in for tutoring and I'd be happy to go over any particular method that you want me to more in depth. Happy practicing.